Welcome to Minute Lectures. This course is about mechanics of deformable bodies or strength of materials. Be guided that there are timestamps below, so feel free to jump right into your desired topic. In this session we will tackle about the concept of stress. It comprises the following topics: Introduction, equilibrium of a deformable body, stress, average normal stress in an axially loaded bar, allowable stress design, and last, limit state design. In this video, we will only go through the first three topics. The other three will be available in another video. Let's proceed to the introduction. Under the introduction are stress and strain. To define stress, it is associated with the strength of the material of the body. Strain, on the other hand, is a measure of the deformation a body undergoes. Now, we'll go through the equilibrium of a deformable body. It is comprised of external loads, support reactions, equations of equilibrium, and internal resultant loadings. External loads has two subtopics: surface forces, which branch further to concentrated force and linear distributed load, and the other, body force. Support reactions has a single branch, reactions, while internal resultant loadings has branches of normal force, shear force, torsional moment or torque, and lastly, bending moment. External loads can either be a surface force or a body force. Surface force occurs when there is a direct contact of one body with the surface of another. When the surface force acts in a small area with the body in contact, it is a concentrated force. Linear distributed load when applied along a narrow strip of area. Body force, on the other hand, is a force a body exerts on another without direct contact. Examples include Earth's gravitational effects or its electromagnetic field. Next is the support reactions. Reactions are surface forces that develop at the supports or points of contact between bodies. Reactions vary on the type of connection. As a general rule, if the support prevents translation in a given direction, then a force must be developed on the member in that direction. Likewise, if rotation is prevented, a couple moment must be exerted on the member. I will show you a table on the types of connection and its corresponding reactions. Feel free to take a snap. Let's proceed with the equations of equilibrium. It occurs when there is the balance of forces preventing translation or acceleration. The equations may be a summation of forces or a summation of moments. Both of them are equal to zero since they are in equilibrium. Last is the internal resultant loadings. They are resultant loadings that act within a body. In order to obtain them, it is necessary to make an imaginary cut straight through the body and consider the plane area the cut makes. Internal resultant loadings differ on the plane area where it acts. Normal force acts perpendicular to the area. Shear force lies in the plane area. Torsional moment or torque, an external load also perpendicular to the plane area but tend to twist. And lastly, bending moment, external load that tend to bend the body about an axis lying in the plane area. Now we'll proceed to the final topic of this video, stress, under which are the assumptions: normal stress, shear stress, general state of stress, and units. There are two branches under the assumptions: continuous and cohesive. Also, two for normal stress, which are tensile and compressive stress. Stress can be described as the intensity of a force acting on a specific plane. This plane is obtained by sectioning a part of the body, which was shown in the topic of internal resultant loadings. As we make sections in the body, it is important to make assumptions regarding the properties of materials of the body. First, the body has to be continuous, which means there is a uniform distribution of matter throughout the body, having no voids, or in other words, continuum. Second, the body is assumed as cohesive, where all portions of the material are connected together without cracks or separation. Before proceeding, let's consider an illustration to have a better grasp of the subject. Consider a sectioned area of a body. Now, we'll consider a smaller area in the plane and denote it as change of A. Acting on change of A is a change of force F, which could be divided into three components: change of Fz, which is normal to change of A, and change of Fx and Fy, which are tangent with respect to change of A. Let's proceed to the normal stress. Considering the illustration beforehand, The force component normal with respect to the area is change of Fc. Normal stress uses the symbol sigma, and to make an equation for normal stress, it is the limit of change of Fc all over change of A as change of A approaches zero. There are two forms of normal stress. Tensile stress, which tends to pull or acts away from change of A, and compressive stress, which pushes or acts toward change of A. Next is shear stress. Shear stress, denoted by the symbol tau, lies in the plane area, or in other words, tangent. Again, considering the illustration, two forces are tangent, change of Fx and Fy. To make an equation for the shear stress along the x-axis, it is the limit of change of Fx all over change of A as change of A approaches zero. The z in the subscript specifies the orientation of the area. Same goes for the equation of shear stress along the y-axis. Now, we'll go through the general state of stress. It is when the body is further sectioned, creating a cubic volume element. Also, it is characterized by three force components acting on each face of an element. To give an illustration, we'll have forces facing towards z-axis, x-axis, and y-axis. Each of them can be broken into three force components and have different orientations on each of their normal and shear stresses. So there will be normal stress along z direction, x direction, and y direction. Same goes for the shear stresses on each plane. Last in this topic are the units. As illustrated in the equations before, stress is the quotient of force per unit area. The units can either be in pascals, Newton per square meter, or psi in the English system. We can say that stress has the same units with pressure, but differs in the range of physical applications. That is all for this session. Stay tuned for the continuation of this lecture. So please consider to like, subscribe, and turn on the notifications to stay updated. I want to hear your thoughts about my lecture, so if you have any questions or clarifications, don't hesitate to comment down below. Or perhaps you have a suggestion to improve my discussion. Let me know about it. Time is up for this minute lecture.